Well, all that's left to section 13 at this point is the three examples at the end, starting with the one that says compression stroke on a diesel engine. So that's number 4. So the question gives us, it doesn't give us the initial and final volume, but it gives us the ratio between them, which is actually all we need, as you'll see when I write it out. And it gives us the initial temperature and asks for the final temperature. So we need a relationship between temperature and volume. And for an adiabatic process, okay, and I should probably explain that. An adiabatic process, again, is one where there is no heat flow. Now, realistically, in an internal combustion engine, either a diesel or a gas engine, either one, yeah, a certain amount of heat escapes. Otherwise, you wouldn't need the cooling system, the radiator and all of that. But each individual stroke of the piston, if you're driving down the road in an engine that's going 2,500 or 3,000 RPMs or something like that, figure out the amount of time it takes for one stroke of the piston. And in that small amount of time, very little heat has a chance to escape. Now, there's a cumulative effect as you run the engine minute after minute, and that's why you have to have a cooling system. But on one single stroke, well, it's not perfectly true. It's like the frictionless surfaces we always talk about in the first course, but to some kind of approximation anyhow, we can think of it as being an adiabatic process. Okay, so that's the rationale between, it says in the question it's adiabatic, but that's why it's a realistic thing to assume. And in an adiabatic process, this is just about the last thing in your notes from the previous class. Well, it says T times V to the gamma minus 1 is a constant, which means if you calculate that quantity for some initial set of conditions, it'll be equal to what you get if you calculate it for some final set of conditions. Okay, it remains constant. So we've got, for the initial temperature, well, here's one place where I would pretty likely catch a lot of people. It says 20 degrees Celsius. So people go sticking 20 in there, and it's, I'm going to try turning this a little and seeing if it keeps the focus from bouncing around like that. No, that did not help. Well, you can read it most of the time, I guess. Stick 20 degrees in there, that's wrong. Just like in the ideal gas law, T is the absolute temperature. In all of these relationships, the internal energy of a gas or anything with a T in it, that's the absolute temperature. So 293 kelvins. And where I got that from is 20 degrees Celsius plus 273. Okay. Now, the question doesn't tell us V1, so I have to keep calling it V1 to the gamma. Gamma, once again, is the ratio of the specific heats, Cp divided by Cv. Okay. Now, there's a table on one of the back pages of your formula sheet that has 3 columns in it. One's for Cp, one's for Cv, but to save you the trouble of having to divide them by each other at times like this, there's a third column, and that third column is gamma, the ratio of the numbers in the other 2 columns. This question says the gas we're talking about is air. And you look in the table, you don't see air. But hopefully you're aware that air is basically a mixture of oxygen and nitrogen, okay? 99% of the gas molecules in your lungs right now are either oxygen or nitrogen. Most of the rest is argon. So you look in the table, and gamma for nitrogen is 1.4. Gamma for oxygen is 1.4. So if you do the appropriate sort of weighted average between 1.4 and 1.4, guess what? You get 1.4 minus 1, because you got the minus 1 there. T2 is the unknown we're looking for. Now, as I said, we don't actually know the initial and final volume, but we're told that this engine has a 20-to-1 compression ratio. So that means that V2 is equal to 1/20th of V1. And that's to the same exponent. So we've got 293 times V1 to the 0.4 power equals T2 times V1 to the 0.4 power over 20 to the 0.4 power. And if you divide both sides of the equation by V1 to the 0.4, you got V1 to the 0.4 divided by V1 to the 0.4. Here you got V1, or I guess, yeah, right, V1 to the 0.4 divided by V1 to the 0.4 there. It drops out, okay? So all the answer is affected only by the ratio between the volumes. If you've got an engine with little tiny cylinders like that, or if you've got some enormous diesel engine that's powering a ship or something like that, it's the same. So T2, we have 293 times the 20 to the 0.4 power. And if you calculate that, it's about 3.314. So T2 comes out 971 kelvins, which, if the question just said find the final temperature, you could call that the answer and go on to the next question. But it says find the final temperature in degrees Celsius. So you have to take the 273 back off again. And the answer is 698. Or maybe in more familiar terms, 1,288 degrees Fahrenheit. For all practical purposes, 1,300 degrees Fahrenheit, which is red hot, okay? This, as it says somewhere in this, well, no, actually it doesn't say it somewhere in that paragraph, but I'll get to that in a moment. But this is the reason diesel engines don't need spark plugs, okay? A gasoline engine has a compression ratio that might be 8-to-1 or 10-to-1 or something in that general neighborhood. But diesels are built a little heavier, and they have significantly more compression. So the gas gets hot enough just from being compressed, so that that's hot enough to ignite the fuel. Okay, you don't have to have any spark plugs. Where all that comes from, by the way, is when the gas is compressed. Okay, the The piston rams up into the gas and squishes it down to this tiny little final volume here. As it compresses the gas, it's doing work. And in that way, it adds to the internal energy. Remember, the internal energy is proportional to the temperature in a gas. The work done, because there is no heat flow, that's what the word adiabatic means in the first place, but there's work being done on the gas as it's compressed. And that's where all of this internal energy comes from that makes it so hot. Now, what it does say here in this paragraph is that these same principles I've been talking about, I've been kind of talking about engines, but they're also involved in refrigerators and other heat pumps, such as an air conditioner. You could, if you were seriously determined, it would be a miserably inefficient device, but you could, in principle, build a refrigerator that worked with air as the refrigerant. As this example here illustrates, compressing a gas runs the temperature upward. Well, it kind of follows that if you reversed the process and expanded the gas, that would let the temperature down. Okay, so you have whatever you're using for a refrigerant. Most refrigerators use some member of the Freon family. I guess there's a few specialized situations where they still use ammonia. But anyhow, whatever you're using for the refrigerant, you compress it, which makes it hot, raises the temperature. And then you circulate it around through some coils of tubing somewhere on the outside of the refrigerator, usually along the back is where it goes. And, metal's a good conductor of heat. The refrigerant gives off heat through the walls of this metal tubing until it's down to room temperature or so. And then once it's cooled off like that, then you let the gas expand, which lowers it below room temperature. And then it circulates through some more coils of tubing on the inside of the refrigerator, absorbing heat from in there. Then it returns to the compressor and the cycle repeats. Now, in any practical refrigerator, these gas law type of things are only part of the picture. A good refrigerant, such as Freon, has a boiling point that's fairly close to room temperature. And of course, boiling points are sensitive to pressure. As I've probably mentioned before, it's not hard to make water boil at 70 degrees Fahrenheit, room temperature. You just put it in a bell jar and start pumping the air out. And when the pressure gets low enough, it starts to boil. So when you compress the Freon, it not only raises its temperature, it also squashes it together into a liquid. Okay, in the low pressure part of the system, the Freon's a gas, but in the high pressure part of the system, it's a liquid. So you compress it, which liquefies it and also warms it up. It goes through the coils of tubing outside. It then expands. There's just a tiny little capillary tube that separates the high pressure part of the system from the low pressure part of the system. The Freon goes through there into some tubing on the inside of the refrigerator, a part that's called the evaporator. And guess what it does in there? Because of the low pressure, it changes back into a vapor. Well, evaporation is a cooling process. That's why your body sweats on a hot day, okay? As the water evaporates off of your skin, it carries heat away and keeps you from overheating that way. And there's a sort of a similar thing going on inside the refrigerator. So it evaporates, which is a cooling process. The change in pressure and the change in state lowers the temperature, and it circulates around in there for a little while, returns to the compressor, and pumps heat from the inside of the refrigerator to the outside of the refrigerator. That's a little more complete picture of what's going on, but the this kind of thing is part of it anyhow. I think there's a question in the homework about, could you cool off your kitchen on a hot day by leaving the refrigerator doors open? And that's probing at whether you understand that a refrigerator or an air conditioner is a heat pump. All you do is you pump heat from the inside of the refrigerator to the outside of the refrigerator. Well, as far as cooling off the kitchen goes, if both the inside of the refrigerator and the outside of the refrigerator are in the kitchen, then you are pumping heat from the kitchen to the kitchen, which is not going to make it any colder in there. And in fact, it'll gradually warm it up because the motor that's running to run the compressor gives off a little bit of heat. And anyhow, that's number 4, together with some applications of these types of principles. So we come to number 5. So we have an old style steam, well, it doesn't have to be a locomotive. Steam engines were used for a lot of stationary purposes also at one time. But we've got about a gallon of steam, 0.004 of a cubic meter, as the original volume before the piston moves down the cylinder and the steam expands. 250 degrees Celsius. First of all, you think of 100 degrees Celsius as being the boiling point, but as I just got done saying, boiling points depend on the pressure. And inside of a boiler, where you might have 20 atmospheres worth of pressure, that significantly raises the boiling point. Furthermore, a lot of steam engines had superheaters that would raise the temperature of the steam even further above the boiling point. So we've got 250 degrees Celsius, and that's the pressure, and it enters the cylinder, and it pushes the piston down the cylinder, turning the wheels or running whatever kind of machinery. If you ever get a chance, it can be kind of interesting to go to the gas and steam show that they have over in Alexander sometime in September, I think, because they've got some of the old steam tractors. I haven't gone to it for years, but they've got some of the old steam tractors from like 100 or 120 years ago. And the thing is just parked there, and it's got this big, long flat belt, 30 or 40 feet long, running up from the power takeoff on the thing. And it's running a big buzz saw, okay? And there's a couple of burly looking guys there sawing boards off the side of a log using this thing just to show how it was done in the old days. It also kind of illustrates why in the old days a lot of guys were walking around without all their fingers anymore, because all this stuff out in the open, it would never meet OSHA standards today. But anyhow, whether you're running a sawmill or a locomotive or whatever, the piston goes down the cylinder until it reaches basically, the boiling point. You get it any colder than that, it's going to turn into water. It won't be steam anymore. Once again, we're going to assume it's an adiabatic process. It's kind of an approximation, but if this happens fairly quickly, it's not an unreasonable approximation. So how much work is done? There's a couple of ways of doing this. I'm going to do it with the first law. So the change in the internal energy is Q plus W. Okay? W is what the question asks for. Q is equal to 0 because it's adiabatic. That right there is the definition of what adiabatic means in the first place. Q equals 0 is what the word means. So if I can figure out how much the internal energy of this gas changes, that would be the amount of work it does, the amount of energy that it delivers to the buzz saw or whatever it is that's being powered by this thing. Well, I said somewhere here in section 13 that for any kind of process, adiabatic or anything else, the internal energy change is equal to N times CV times delta T. The constant volume specific heat of steam is something you can look up in your reference handout. And the temperatures are given in the question. So this is all going to come down to determining how many moles of steam are in that cylinder. And as you might have guessed, because that seems to be what I always grab when I'm looking for some sort of additional constraint on the variables, we're going to get N out of PV equals nRT. And I'm going to apply that to the initial conditions simply because I know more about them. It tells me a lot about, I've got the initial volume, I've got the initial pressure, I've got the initial temperature. All I've got for the final conditions is the temperature. It doesn't tell me anything else. So we're going to go with, that's why all the little subscripts are ones. Solve it for N because that's the thing I need. And put the numbers in. Initial pressure, 20 atmospheres. Well, we need SI units. Atmospheres is not going to fit in with the units on the other numbers around it, like the gas law constant here. If it's, there's probably some handbook where you can look up a value for the gas law constant that's based on atmospheres instead of pascals. But the value you find on your formula sheet, 8.314, that's in SI units. So everything else around it's got to be SI units also. And assuming standard atmospheric pressure, because the question doesn't say anything to the contrary, 1.013 times 10 to the 5th pascals. A pascal, once again, is a Newton per square meter. Okay, atmospheres times pascals per atmosphere gives me pascals. So the thing in the brackets there, that would be my initial pressure. Initial volume, shouldn't have made my line so long. That we're given. There's no fooling around needed with that. That's in cubic meters. Gas law constant in the units that we work in, 8.314. And here's the other place where you might go astray. Same thing I said about this previous question. You got to have degrees Kelvin. So 523 kelvins, which I got from 250 plus 273. Okay, so that equals 1.8 0.64 moles. Okay. Now we can wrap things up. So N, 1.864 moles. CV, 27.0. That's joules per mole per Kelvin. And the temperature change, final minus initial, I think I explained when I was doing an earlier example how that if you're talking about temperature changes, Celsius and Kelvin are interchangeable. Okay, both scales have the same size degree. So if something changes temperature by 145 kelvins, it's also changed temperature by 145 degrees Celsius, because 273 gets added to each of these, so it drops out. So that times that times that, and we have minus 73, almost exactly. It's like 7298 or something like that, rounding off to three significant figures, 7,300 joules. So I mentioned there was more than one way of doing this. The alternative, I'm not going to run through the whole problem again, but just as a sort of a parenthetical comment, the other way of getting it is work is equal to minus the integral of P dV. And for P, you can make some substitutions for the expressions for adiabatic processes into there, and I'm not going to get into the details. It comes out slightly different, a little higher, more like 7,500 joules instead of 7,300, and that's because some of the constants are a little on the approximate side. You know, you go to look up a specific heat, and or any of these kinds of things, expansion coefficients, anything like that. You look it up in one reference and you get one value, and you look it up in a different reference and you get a slightly different value because, you know, somebody measured it in 1947 and they got this, but somebody else measured it in 1959 and they got that, and you know, it's like they got 0.12 when the one person did it and they got 0.11 when the other person did it, and so there's something like that going on to cause slightly different answers depending on the approach you take here, but you'll get something in the same ballpark anyhow. Number 6. Well, having done one that involves an adiabatic process, let's not get too fixated on that. Let's do an isobaric process and an isothermal process. The gas expands from 2 liters to 7 liters, gives the initial pressure. So first of all, isobarically. Of course, anything's always easier when stuff is remaining constant. An isobaric process means constant pressure. If the pressure is constant, you know, I just put on the bottom of the previous page here, integral of PdV, but if the pressure is remaining constant, there's no need to divide things up into infinitesimals and then add them all up. Instead of a huge number of little tiny rectangles underneath your graph, you can put just one big rectangle under the graph, and that's what this would be if you drew a picture of it. Okay, so the word isobaric means constant pressure, and therefore it's just this. Pressure is 4.0 times 10 to the 5th pascals. Change in volume. Oh, almost forgot the minus sign. Now, a liter is not the standard SI unit for measuring volume, okay? A pascal, once again, means a Newton per square meter. So therefore, volume has to be in cubic meters, because you see how that'll work. Some of the 2 out of these 3 meters get canceled by those, leaving you with newtons times meters, which is the definition of a joule, which is the SI unit for work. So liters is no good, got to have cubic meters. And the 2 liters that you had initially is 0.002. And so you've got 5 times that, which comes out 2,000 joules. Negative because we're calculating the work done on the gas, and if it's expanding, work is in fact being done by the gas. Part B. Well, now for this you would have to integrate, except I already did. That was an earlier example. I'd have to flip back through here to see if that was the number 2 or number 3, but near the beginning of this section, it said find the work done in an isothermal process. And the answer to that, oh, it's written right here, example number 2. So in an isothermal process, and this formula would be only for an isothermal process, okay, so in that earlier example, I did the integral of PdV for you, and this was the result. So all we have to do is drop in numbers, except the question doesn't say anything about temperature or the number of moles, but once again, it's PV equals nRT to the rescue. It's the initial pressure that the question gave me. So let's consider the initial conditions. P initial, V initial equals NR times T initial. Well, the word isothermal means the temperature is constant, and R is always a constant, and N is a constant as long as you don't pump any more gas into the cylinder or let any out. So because it's an isothermal process, nRT does not change. So P initial V initial equals P final, or P final. Or no, never mind. I'm going off in the wrong direction with that. Pretend I didn't say anything. If this was a professional video, I'd cut that part out. But it's not, so live with it. initial. I'm just all of a sudden having problems. Okay, so the point of this was that nRT, which never changes, okay, it's constant throughout the whole process, would be equal to P times V at any time that we happen to know P and V, which would be at the beginning of the process. And now I've got something that I can drop numbers into. Initial pressure, 4.0 times 10 to the 5th pascals. And initial volume, 0.002 of a cubic meter. Same initial conditions we had in part A. Natural log. Well, when in doubt, convert to standard units. 0.002 divided by 0.007 will work just fine. But if you're feeling lazy, 2 liters over 7 liters. See, the units drop out anyhow. They could both be in pounds per square inch. It doesn't matter. All that you're worried about is the ratio. Okay, since the units cancel each other, you can leave it in liters if you want. This part here, the natural log, comes out negative. Anytime it's the log of something less than 1, it'll be negative. No, less than 1, more than 0. 1 point. Yeah, I'm just having a terrible time today. I don't know. 1.25, and of course it keeps on going. 1.25276. Multiply it by those other 2 numbers. And normally I would round off to 3 significant figures because that's kind of the standard that we've been using throughout the course. But rounded off to 3 significant figures, this would be 1,000. And I didn't want to give people the impression that there was any particular reason this number should be half of that number, because it's not half of that number. It comes out fairly close, but that's not an exact kind of thing. And with significantly different numbers, it might not be anywhere close to a 2-to-1 ratio. So starting with the same conditions, expanding to the same final volume, yet significantly less work is done if it does it at a constant temperature instead of a constant pressure, which you can see if you sketch the graphs. Remember the PV diagrams? Both processes started, let's say, right there. Let's say that's 7 liters, and let's say that's 400,000 pascals. Now, in a constant pressure process, so this would be part A of the question. You go right straight across. It remains a pressure of 400,000 pascals, horizontal line. For a constant temperature process, on the other hand, it follows one of those isotherms that I was talking about 1 or 2 classes back. One of those y equals 1 over x kind of things, rectangular hyperbola. And remember that the work done is the area under the graph. So, you know, between there and there is significantly less area underneath graph B than there is underneath graph A. And that's reflected in the fact that there's a lot less work done in case B than there is in case A. And that's about everything I can think of to say about section. Well, let's say that's a good place to quit. Everything I could possibly think of to say, that's probably not true. But next recording, we start section 14.